Okay, we are getting ready to start chapter 4, which is the beginning of our study of trigonometry. And we're going to be studying trigonometry for most of the rest of the year. There are 4 chapters in the book on trigonometry, and we are planning to cover all of those. I'm hoping we can cover a couple of other chapters too, but I'm not sure if that's going to happen. So we're going to just start out with very foundational definitions and things like that to make sure that you know exactly what angles are and how they're measured and how we use those. So that's where we're going to start. We're going to start with the ray. You may recall, you've learned about this before, I'm sure, that a ray is part of a line. It's made up of an end point and all the points to one side of that end point. So it's kind of like a half of a line. And when we name a ray, we always start with the end point and name another point on the ray second. So you could write this ray on the left could be ray PQ. You start with the end point, and then the ray on the right we could call ray QP. An angle is formed by rotating a ray about its endpoint. The starting position of the ray is called the initial side. Of the angle, and the final position of the ray is called the terminal side of the angle. The common end point of the two rays, so right here is A, is called the vertex. You could call the above angle angle A, since there's only one vertex here, there's only one angle in this picture, so it would be perfectly fine to call that angle A. You could also call it angle CAB or angle BAC. As long as the vertex comes in the middle of the name, that's fine. And you could even call it by its measure. You could call it angle theta. Often angles are named with Greek letters like theta or phi, some people say phi, or alpha, those kinds of letters. Gamma, we'll mostly be using theta. An angle is in standard position if its vertex is at the origin, 0, 0, with its initial side on the positive x-axis, so over here, 90 degrees, 180, 270, and then 360. And hopefully you remember this from Algebra 2. So the initial side is on the positive x-axis. And we would say that this angle is in standard position. All right, the measure of an angle quantifies the direction and amount of rotation from the initial side to the terminal side. So the measure of an angle is positive if the rotation is counterclockwise, and the measure of the angle is negative if the rotation is clockwise. One unit of measure for angles is called the degree. One full rotation is 360 degrees. That was defined by the ancient Babylonians. So 360 degrees is one full rotation. So a degree is just 1/360th of a full rotation. Okay, so you can see some angles here. This angle is 45 degrees because you start on the positive x-axis and you rotate counterclockwise 45 degrees. This angle, negative 270, you're starting at the positive x-axis, you're rotating clockwise, so you're going 90, 180, and then all the way around to 270 degrees. There's 90 degrees in each quadrant. It's negative because it's clockwise. Over here, you've got 30 degrees, which is starting on the positive x-axis. You're rotating 30 degrees in the counterclockwise direction. Negative 150, you're starting on the positive x-axis and you're rotating 150 degrees in the clockwise direction. If the measure of an angle theta is 30 degrees, we can denote the measure of theta as m of theta equals 30 degrees, or just theta equals 30 degrees, and that's usually how I would write it. A few key terms related to angles. A right angle measures 90 degrees. That's exactly 1/4 of a turn. A straight angle measures 180 degrees. That's half a full turn. An acute angle is an angle between 0 and 90. An obtuse angle has a measure between 90 and 180. If the sum of the measures of two angles is 90, we say the angles are complementary. And notice it's complementary, not complementary. If the sum of the measures of two angles is 180, we say that the angles are supplementary. A degree can be divided into 60 equal parts called minutes. So we can represent minutes with MIN or with that little apostrophe right there. A minute can be divided into 60 equal parts called seconds. And we're not talking about time here. We're talking about pieces, parts of a degree. So each degree can be broken into 60 equal parts called minutes, and each one of those minutes can be broken down into 60 equal parts called seconds. And for seconds, you can have SEC or that little quotation mark. All right. So 1 minute is 1/60th of a degree, or you can write it 1 minute with the little apostrophe is equal to 1/60th of a degree. 1 second is 1/60th of a minute, or 1/3600th of a degree. Or you could write 1 with the little double apostrophe, and that equals 1/60th of a minute, or 1/3600th of a degree. Okay, 74 degrees, 42 minutes, and 15 seconds would be denoted as 74 with the degree sign, 42 with the apostrophe, and 15 with the quotation mark. Writing an angle this way is DMS, degrees, minutes, seconds. All right, so if we wanted to convert 74 degrees, 42 minutes, and 15 seconds to degrees, first of all, 74 is already in degrees, so we don't need to worry about that. Remember, there are 60 minutes in a degree, so we could write 1 degree over 60 minutes. This is just like unit multipliers. You've been doing that for a long time now. We're going to use these unit multipliers. So we can use the unit multipliers from the previous slide. 1 degree for every 60 minutes. So to change that 42 minutes to degrees, this is what we would do. So the minutes would cancel and we would end up with 42 over 60 degrees. So we've got that. And then the 15 seconds, we can change that to minutes by saying that there is 1 minute in 60 seconds. And then we can change that to degrees by saying that there's 1 degree in every 60 minutes. So you can see that the seconds are going to cancel and the minutes are going to cancel, and you're going to end up with degrees. So that's going to be 15 over 3600 degrees. So if you add up 74 plus 42 over 60 plus 15 over 3600, punch that into your calculator. You will not need to use your parentheses for this because your calculator is going to follow the order of operations. So when you hit 74 plus 42 over 60, it will do the division first. It won't do the addition first. So you don't need to worry about that. So 74 plus 42 over 60 plus 15 over 3600 equals 74.7042 degrees. Or you could just put the little circle. Okay, example 2, convert 159.26 degrees to DMS form. All right, the 159 is already in degrees, so we don't need to do anything with that. The 0.26 is what we need to change to minutes and seconds. So first we can change that to minutes. So 0.26 degrees, we can multiply that 60 minutes in 1 degree. 0.26 times 60 is going to be 15.6 minutes. So we can go ahead and put that 15 minutes over here. So 15 minutes. And now we just need to change the 0.6 to seconds. So 0.6 minutes times 60 seconds in 1 minute. So that's going to be 3.6. That's the last thing we're going to write over here is 3.6. So that would be how we would write this in degrees, minutes, seconds. Okay, another way to talk about the measure of an angle is to use radian measure. A central angle that intercepts an arc on the circle with length equal to the radius of the circle has a measure of 1 radian. So if the radius is this r here, if we were to take that radius and bend it and wrap it around the circle so that the length of that arc is now r, the angle that you get when you intercept that arc with 2 radii, and you've got that angle in between, theta, that is what is called 1 radian. So the angle, we would measure that and call it 1 radian. And also the length of that arc can also be called 1 radian. The tricky thing about radians, they're a little hard to think about because, for one thing, the number of radians in one rotation is not a whole number. So if you go around the circle, starting right here, and you go 1 radian at a time, so that's 1 radian, and 2, 3, 4, 5, 6, and then you get a little bit more right here, but it's not a full radian. So looking at the picture, you can see there's a little more than 6 radians. And the question is, well, how many exactly is that? It's 6 and a little more. And what you find out is, and what you may know if you sit and think about it for a while, is that it is going to be exactly 2 pi radians. So the number of radians around a circle is an irrational number, and that is 2 pi radians, which is about 6, but a little more, because pi is about 3.14. 2 times 3.14 is about 6 and a little more. So why is that true? And that is just because the circumference of a circle is equal to 2 times pi times the radius. So the distance around a circle is 2 pi radians. And so the angle that you go around would also be called 2 pi radians. 360 degrees, in other words, is 2 pi radians. All the way around the circle, 2 pi radians, because a radian is a radius. Therefore, 2 pi radians is 360 degrees, and half of that, pi radians, is 180 degrees, or halfway around. So 1 revolution, 2 pi radians, 1/2 revolution, pi radians, 1/4 of a revolution, 90 degrees, is pi over 2 radians, and 3/4 of a revolution is 3 pi over 2, or 270 degrees. So you can change radians to degrees just by knowing that 1 full rotation is 360. Okay, so let's convert from degrees to radians. So we're going to do this again, kind of like with unit fractions. So if I want to convert from degrees to radians, 210 degrees, I can just multiply that by 2 pi radians in 360 degrees, or to make it simpler, I could multiply it by pi radians for every 180 degrees. So the degrees will cancel, and I'll just have 210 pi over 180. When I convert from degrees to radians, I do not want to multiply this out in my calculator. I want to just write it as a reduced fraction that has pi in it. So I've got 210 degrees over 180 times pi. And if I reduce that, you can knock off these two zeros. And then 21 over 18 is just going to be 7 pi over 6. And that's how we would talk about radians. We would say 7 pi over 6 radians. Okay, so you would start with negative 135 degrees, and you would multiply that by pi radians over 180 degrees. So that's negative 135 pi over 180, and since 45 goes into 135 three times, so that's negative 3 pi over 4. And that's how you would leave it. You do not need to write radians next to it. That's just the way we write radians. So negative 3 pi over 4 radians. All right, converting radians to degrees, very similar. You just use the same unit multiplier. So you just flip it upside down because you want the pi's to cancel. So if you have pi over 2 radians, you would say that there are 180 degrees in pi radians, which would make the pi's cancel. And you would just end up with 90 degrees. Pi over 2 is the same thing as 90 degrees. Negative 4 pi over 3 radians. Again, you're going to multiply that by 180 degrees in pi radians. The pi's will cancel, and you will end up with negative 4 times 60 degrees, and that's going to be negative 240 degrees. Okay, so two angles with the same initial and terminal sides are called coterminal. And what I mean by that is that they start on the positive x-axis and then they rotate some number of degrees or radians, and they end up in the same place, even though they may have gone a different number of degrees or radians. For example, if you look at this first picture on the left, this is 390 degrees. So the angle starts on the positive x-axis and then it spins all the way around and comes back to rest on that terminal side. It's the same thing that the next angle does. It starts on the positive x-axis and it goes around and then around and then ends up at the same place. So 390 and 750 are said to be coterminal because they start in the same place and they end in the same place, even though they may do, something different in between. Same thing with negative 330. It is starting on the positive x-axis. This time it's going to turn clockwise because it's a negative angle, and it also ends up right there where the other two ended up. So these three angles are called coterminal because they all start and end in the same place. Their initial sides and terminal sides are the same. And you can see that the angle that is less than 360 that they all are coterminal with is 30 degrees. Because if you start on the positive x-axis and you rotate counterclockwise 30 degrees, you end up on that terminal side. So all three of these angles are coterminal with 30 degrees. So this angle right here is 30. And so what you find out is that you can write all of these measures. All of these measures are just 30 degrees plus or minus some multiple of 360. You can spin around as many times as you want to, but if you end up at that 30-degree angle, then you're coterminal with 30. So let's look at an example where we want to find the angle between 0 and 360 that is coterminal with the angle that we're given. So we've got theta equals 960 degrees. So we want to find an angle between 0 and 360 that is coterminal with that angle. Now, if we look at what's happening on the circle here, if we're starting here at 0 degrees and we spin 960 degrees in the positive direction, which is counterclockwise, then we're going 360 and then another 360, which would be 720. And do we go another time around? I don't know. Let's see. 360 times 3 is 1,080. So that's more than 960. So we're not going to spin around 3 times. We're going to spin around 2 times plus some more degrees. So 960, if you spin around twice, 2 times around is 720, 360 plus 360. And 960 minus 720 is just 240 degrees. So the angle between 0 and 360 that is coterminal with 960 is 240 because you spin all around the circle twice for 720, and then you go another 240 degrees, so 90, 180, and then 60 more to get to 240. So basically, you're just subtracting some multiple of 360 or adding some multiple of 360 to get to the angle that is between 0 and 360, and that is the angle that's coterminal with whatever angle you have. So with negative 225, again, now this is a negative angle, but I want to get the angle that's between 0 and 360 that has the same terminal side. So negative 225, if I start here at 0 degrees, and I am going in the negative direction, which is clockwise, I'm going to go 90, 180, and how much further do I need to go to get to 225? Negative 180 and another negative 45. That's what puts me at negative 225. But what I want to know is, what is this angle? The angle between 0 and 360 that has the same terminal side as negative 225. Which angle between 0 and 360 is going to make me end up in the same place? What I'm going to do is just add 360 to this number until I get to an angle that is between 0 and 360. So if I add 360 to this, I get 135. And so that is this angle right here that takes me from 0 to 90 and 45 degrees more into the second quadrant. And that is the angle that has the same terminal side as negative 225. So if you have a positive angle, you're going to subtract 360 from that until you get an angle between 0 and 360. And if you have a negative angle and you want an angle between 0 and 360 that's coterminal with that angle, then you will add 360 to it until you get an angle between 0 and 360. Because basically what you're doing is you're just getting rid of those extra spins. And this is just kind of a repeat of what I was just saying, is that two angles in standard position are coterminal if their angle measures differ by a multiple of 360 or 2 pi radians. All right, so if I want to find an angle that's coterminal to theta on the interval 0 to 2 pi for this first part right here, negative 5 pi over 6, all I need to do is add 2 pi to this and see what that gets me. So I'm going to add 2 pi, and that's going to be negative 5 pi over 6 plus 12 pi over 6, and that's going to give me 7 pi over 6. So that is going to be my angle that is coterminal to negative 5 pi over 6 because it's between 0 and 2 pi, and that's all I had to do was add any multiple of 2 pi or subtract a multiple of 2 pi. So now I've got theta equals 13 pi over 2. This is more than 2 pi, so I'm going to need to subtract some multiple of 2 pi from this to get down to an angle between 0 and 2 pi. So if I subtract 2 pi, that's going to be 13 pi over 2 minus 4 pi over 2, and that is equal to 9 pi over 2. So you can see that I'm going to have to do that a couple more times, since 2 pi is the same thing as 4 pi over 2. To get this down to a value that is between 0 and 2 pi, I'm going to need to subtract another 2 multiples of 2 pi. It's going to be 9 pi over 2 minus 4 pi, which is the same thing as 9 pi over 2 minus 8 pi over 2, and that's going to be pi over 2. So this angle, 13 pi over 2, is coterminal with pi over 2. So another way you could think about this, you could write this fraction as a mixed number, which is something we don't normally do, but 13 halves is the same thing as 6 and 1/2. So you could say 6 and 1/2 pi. So that means you've got 2 pi, 2 pi, 2 pi, so 3 spins around the circle, plus another half pi, which is pi over 2. So that's another way that you could think about it. You're just getting rid of those extra spins around the circle. Okay, we're going to look at arc length. An arc is just a fractional part of the circumference of a circle. So once we find out what fractional part it is, we can just multiply that fraction by the whole circumference, 2 pi r, to find out the length of the arc. So an arc, like I said, this S right here is just a piece of the circumference of the circle. So the whole circumference is the whole way around. This is just some fractional part of the way around. So theta is a fractional part of one rotation. So theta over 360 would be the fractional part that you have rotated when you rotate from here to here. And so that rotation is the fractional part. If we're talking about degrees, if theta is in degrees, then that fractional part of the circle that you have rotated there is theta over 360. So say you rotated 90 degrees. That'd be 90 over 360, or 1/4 of the way around the circle. And that means that the arc you've just gone through is 1/4 of the whole circumference. So whatever theta is, if it's in degrees, you will use this method. You will say, okay, the length of the arc is just theta over 360 times 2 pi r, which is the circumference, the whole circumference. So the fractional part of the circumference. Theta over 360 times the circumference, which is 2 pi r. If theta is in radians, then the length of that arc is going to be theta over 2 pi times 2 pi radians, 2 pi r, the circumference. And in that case, if theta is in radians, you just end up with the equation, the arc length equals r times theta, radius times radians. Find the length of the arc made by an angle of 105 degrees on a circle of radius 15 centimeters. Just a note, which I'm probably going to repeat in a minute, is that I'm not doing this the way the book is doing it. The book is having you convert your degrees to radians first, and then finding the length of the arc. But I don't see any reason to do that because we're just thinking of this as the fractional part of the circle multiplied by the whole circumference. So I've got a circle. I'm talking about 105 degrees. So here's my circle. I'm going from here to about here. And that's 105 degrees. And I'm trying to figure out what is the length of this arc right here. Okay, well, that arc is a fractional part of the circumference of the circle. And that fractional part is 105 360ths. That's how far around I've gone. And so if I multiply that fraction by the circumference, then I'll know how long that piece of the circle is. So they tell me that the radius is 15 centimeters. So I can plug that in for R. And if I punch all of that into my calculator, I'm going to get about 27.5 centimeters. All right, so determining distances between cities. The Earth, you may know, is not flat. Therefore, long distances on Earth cannot be measured as straight lines. They have to be measured as arcs of a circle because the Earth is approximately spherical and the equator is approximately a circle. So latitude is the angular measure of a central angle centered at the center of the Earth, either north or south from the equator. The North Pole is at 90 degrees north latitude and the South Pole is at 90 degrees south latitude. Okay, so if you take a look at this, well, first of all, you can see on this map, you have all these lines going across. The lines that are going across, the horizontal lines, those are the lines of latitude. And you can see that there are measures over here in degrees telling you how far north or south you are from the equator, which is 0 degrees. Well, that angle is being measured from the center of the Earth. So if you look at this picture of the Earth where you have the center of the Earth right there, so if you come straight out to the equator, you're starting at 0 degrees and then you're rotating north 30 degrees. That is 30 degrees north latitude. So that's what latitude means. All right. Longitude are the lines that are going vertical. They're the ones that are going from the North Pole to the South Pole all the way around the Earth. In that case, the prime meridian, which is a line of longitude, that is considered 0. That is the line of longitude that goes through Greenwich, England, and then it goes through the North Pole and the South Pole and comes around. So with longitude, you're starting at the prime meridian and you're rotating either this way on that circle that lies flat, or you're rotating the other way and you're either going west or east a certain number of degrees on that circle. So with latitude, your circle is standing up and you're rotating from the equator up or down. If you're talking about longitude, your circle is lying horizontal and you're rotating either east or west from the prime meridian. So let's look at an example. Seattle, Washington is located at 47.6 degrees north, 122.4 degrees west on the globe, and San Francisco, California is located at 37.8 degrees north and 122.3 degrees west. All right, so since you can see that they have basically the same longitude, 122.4 and 122.3, really all you need to think about is the latitude because one of them is just due north of the other. So the longitude doesn't really change. So if we want to find out the distance between them, all we need to do is find the length of this arc right here. The equator is here. And so San Francisco is this many degrees up and Seattle is this many degrees up. So since Washington is 47.6 degrees north and San Francisco is 37.8 degrees north, we can just subtract those two angles, see what that angle is. That's going to be this angle here. Now we can use that angle to figure out that distance, that length of the arc. 47.6 minus 37.8. So that's just 9.4 degrees. And so all we need to do now is just find the length of that arc, which is going to be 9.4 degrees over 360 degrees times the full circumference of the Earth, which is going to be 2 pi r. So 2 pi times the radius of the Earth is 3,960 miles. And so now all we need to do is punch that into the calculator. You're going to say 9.4 divided by 360 equals times 2 times pi times 3960, and you're going to get about 649.68 miles. We're just going to round to the nearest mile like it says to do, so that'll be 650 miles from San Francisco to Seattle. And again, this is not the way the book does it. It's slightly different. We're just going to not change our degrees to radians and just remember that an arc of a circle, the length of that arc is just some fractional part of this full circumference. And we're just going to multiply that fractional part by the circumference to figure out what that piece is. Okay, linear and angular speed. The linear speed of an object is just the distance per unit of time. So like a car, miles per hour. It's how far you go over a certain amount of time, meters per second. So the distance you go in miles or meters or inches in a certain amount of time, that's linear speed. Angular speed of an object is measured in units like degrees per second or radians per second. So now we're talking about the speed of rotation. We're not necessarily talking about the distance the thing is going. We're talking about over what amount of time does it pass through a certain number of degrees or radians. Okay, so if you look at this picture of this ceiling fan and you've got these 2 points on there, B and A, if the fan spins around one time, A is going to go further than B will because A is way out on the edge of the fan and it goes through a big circle. B only goes through a small circle. So they both go 360 degrees. They both have the same angular speed, but one of them covers more inches or feet because it's going around a bigger circle. So even though 2 points might have the same exact angular speed, they may have a different linear speed because linear speed is about distance and angular speed is about rotation. So to find linear and angular speed, we will not be using the formulas in the book. We will be using unit multipliers as we did in Algebra 2. Example 9, a ceiling fan rotates at 90 revolutions per minute, RPMs, for a point at the tip of a 2-foot blade. Find the angular speed. The angular speed will be the same no matter what the radius is because we're just talking about rotations or revolutions per minute. All right, so we've got 90 revolutions per minute. And so what we want is a unit multiplier that will get rid of the revolutions and give us just radians per minute, because in your book, when they ask you for the angular speed, they're asking for it in radians unless they tell you different. So we just need a unit multiplier for that, and we have one already because we know that there are 2 pi radians per revolution. So 2 pi radians per revolution over 1 revolution. Revolutions cancel, and I'm going to end up with 180 pi radians per minute. And your book says that you do not need to write radians. You can just say 180 pi per minute. All right. Part B, you want to find the linear speed. Okay. Since they give you the radius in feet, your answer is going to be in feet per minute. So you've got 180 pi radians per minute. And you know that the radian length is 2 feet. Remember, radian and radius would be the same length. So 2 feet per radian. I want the radians on the bottom, so they're going to cancel out. So 2 feet per radian. So my radians cancel. And this time I'm going to punch it into the calculator because I want to know how many feet are we talking about. So 180 times pi times 2. So we're supposed to round to the nearest whole unit. So 1,131 feet per minute. Okay, so we're just to change angular speed to linear speed, and either way, we just want to use the unit multipliers. All right, now the area of a sector. A sector is a pie-shaped wedge of a circle bounded by the sides of a central angle and the intercepted arc. We will think of it as a fractional part of a circle. So we were talking about the fractional part of a circumference of a circle. Now we're going to talk about a fractional part of the area of a circle. That is what is called a sector. All we need to do to find its area is to figure out what fractional part of the circle it is and multiply that fraction by the area of the circle, which is pi r squared. So this is very similar to finding the length of an arc, except now you're finding an area. You're finding the area of a pie-shaped wedge. If theta is measured in degrees, all you need to do is say theta over 360 and multiply that by the whole area of the circle to find that piece of the circle. If theta is measured in radians, then all you need to do is write theta over 2 pi the whole way around the circle and then multiply that by the whole area of the circle, pi r squared, and you will get the area of that fractional part. So this is different from the way the book does it. Yep, we will use the appropriate formula. We will not change degrees to radians first as the book does. So Example 10, a crop sprinkler rotates through an angle of 150 degrees and sprays water a distance of 90 feet. Find the amount of area watered, round to the nearest whole unit. It's 150 degrees out of the whole 360. So this is the fractional part of the circle that this sector represents. 150 out of 360. And now all I need to do is just multiply by the area of the whole circle to get the area of this fractional part. And the area of the whole circle is just 90 squared times pi, pi r squared. So that is going to be about 10,603 square feet. So that is everything from section 4.1. So I want you to really understand what you're doing here and what it all means, and make sure that if you don't, you email me and ask questions and get it figured out. So we will be moving on when we get to class next week.